Let's go back to Pythagoras. This is part 2 of the talk on Birch and Swinnerton-Dyer, and well, really mostly about the congruent number problem. Let's go back to Pythagoras, where we started a while ago. What is the pattern in the Pythagorean triples? I mentioned that there's a pattern. How do you generate them, as opposed to just kind of finding them randomly? And can the same ideas guide us in the congruent number problem? And of course, the answer is yes, but not in a super obvious way. So let me lead you through that. So let's look at the some of the geometry of Pythagoras. This is all about how number theory relates to geometry in interesting ways. We've already got triangles coming in. That's a certain amount of geometry, but we're going to see there's a lot of other geometry to talk about as well. So let's look at a 3, 4, 5 triangle. And I want to I want to talk really about that scaling trick again. We had the scaling trick that, for example, turned the 3, 4, 5 into something that was half as big in each dimension and gave us an area of 1.5. Well, there's a universal version, there's a standard version of that scaling trick where we take the triangle and we scale it down so that its hypotenuse is exactly 1. And so that kind of standardizes the triangle. In particular, what it does is I've drawn a circle of radius 1 here called the unit circle around an origin of coordinates in the xy plane. So I'm putting coordinates on here and I'm putting a circle on here. And by scaling down the hypotenuse to be length 1, I make sure that that point here is on the unit circle. Now let's call the new sides x and y. Well, it's not hard to figure out what x and y are. If I'm scaling this down by a factor of 5, I'm going to scale everything down by a factor of 5. That's similar triangles, to use the official name. But it's really just a scaling factor again. And so x is going to be 4/5 and y is going to be 3/5. They still have the same ratio to each other. That's a characteristic thing about similar triangles. So suddenly I've got a new problem about points on a circle. If I can find cool, interesting points on this circle, that's going to have to do with Pythagorean triples. And what's special about the points on the circle is, once again, if this is x and this is y, or in other words, if the coordinates of this point are x comma y, then Pythagoras now says x squared, that side squared, plus y squared, that side squared, is equal to 1. So that simplified things. Instead of having an equation with 3 variables, it's got it down to 2. That's real progress. And it also tells us that that's the equation of the circle, because that's all the points that I can get with the hypotenuse equal to 1. In this case, this is the point 4/5 comma 3/5. So we've gone from a triangle and that kind of geometry to the geometry of the unit circle, and we've got algebra associated to that unit circle. That's something we're going to see a lot of. So in particular, if I have a Pythagorean triple, I can scale it down to get a point on the unit circle, and these numbers are going to have rational coordinates. That's very significant, because if you pick just a random point on the unit circle, most often it's going to have irrational numbers as its coordinates. Because you have these squares, you're going to get square roots all over the place when you try to solve for x or y. And conversely, if I have a rational point on the unit circle, like 4/5, 3/5, I can just scale it up by the common denominator, scale it back up to the 3, 4, 5 triangle I had before, and I get a Pythagorean triple. Okay, so we've restated the problem in an important way. I've got a certain very natural special curve in the plane, which has an algebraic equation that defines it. It's called an algebraic curve, surprise, surprise. And finding these Pythagorean triples corresponds to finding rational points on the unit circle. Okay, now why is that helpful? Well, here's another piece of geometry that's not something that's obvious, but it's a very cool piece of geometry. Instead of taking a ray going from the origin out through x and y to build these triangles, it turns out to be very useful to shoot a ray or a line from the point -1 comma 0. That's where x is 1 unit left, that's what the -1 means, and y has not gone up or down, that's what the 0 means. This point on the far left edge of the circle. What we do is we can take that and take any point AB in the plane and just connect the dots and see where it intersects the circle a second time. Now, if AB is like over here, it won't intersect the circle again. So let's make sure AB is over here. Well, and in fact, what we're going to do is we're going to make sure we start out with A and B being rational numbers, or even it works if they're just integers. And the claim is that that's going to create a rational point on the circle. So I'm not going to go through the details of that, but I want to talk about some of the general ideas that are going to generalize to the congruent number problem. A line, if we look at the algebra of a line, and I think somebody noted a typo when I did this talk before. A line is very special when you look at the algebra of it. It's an equation that's not only just nice algebra in terms of x and y, but it doesn't have any squares or cubes or anything. Y is to the first power and x is to the first power. Here a and b are given numbers. They're not really variables. X and y are our variables to determine the point on the line. And it's got a linear equation, something with things that don't have anything more than a first power of x or y. It's called a degree 1 polynomial equation. The circle is a degree 2 equation. It's the quintessential example of a degree 2 equation because x and y come in as squares. And what we notice is that at least in this example, in this picture, they're intersecting in 2 points. I claim it's not at all a coincidence that 1 times 2 is this number of intersection points. That's going to be very important later, and I'm going to talk more about it in a little bit. The claim I have, and I'm not going to go through the details of this, but I'll show you the algebra. You can check it yourself. Is that if I start with a and b rational, or integers, actually, to be really simple if you want it, then, and I do this intersection, then x and y are going to be rational as well. Let's see. Turns out that when you do the algebra, when you combine these two equations to do the algebra to find this intersection, you get these explicit formulas. X turns out to be a squared minus b squared over a squared plus b squared. And y is 2 times a times b over a squared plus b squared. That's the part I'm going to just sweep under the rug a little bit. But if you're good at algebra, then it's not super hard to actually solve the system of equations I had before and find this. And these are definitely rational. I'm not doing any square roots or anything like that. I'm just multiplying, dividing, and adding, and that's all stuff that gives rational numbers. And remember, our original goal was to relate that the little x and y, point on the circle, to be able to blow those back up to a Pythagorean triple. And indeed, you can do that. Just multiply by the common denominator. Multiply by a squared plus b squared here, you get x is a squared minus b squared. And y is 2ab, and then the denominator, or the hypotenuse rather, which was equal to 1, that's this distance, you scale it back up to that big triangle, is just what you scaled up by, the scaling factor. It's a squared plus b squared. A really easy piece of algebra to check, if you like algebra, you don't have to check it, is just to check that indeed x squared plus y squared equals z squared. I really love this because we were trying to find things whose squares have a relationship to each other, and the weird thing is we build them out of squares of other numbers. And what's really useful about this is that a and b didn't have to be special. A and b didn't have to satisfy anything weird. They could just be any rational numbers, and they could certainly be integers, and big X, big Y, big Z become a Pythagorean triple. So that's the holy grail of this kind of thing. You have X, Y, and Z that are hard to pick randomly. You can't just pick X, Y, and Z randomly and have it work. It's not going to be a Pythagorean triple. You can't just pick X and Y randomly and have a Z pop out that's going to work. But if you pick any A and B integers, as long as A is bigger than B, so this turns out positive, then this will work. And that's a little bit of a minor miracle. Okay. So for a numerical example, suppose we pick A equals 5 and B equals 4. So geometrically, we pick this to be the point 5, 4. We go 5 units this way, 4 units this way. We intersect it with this special line, which is pretty cool. And then we do the algebra, and we get x, y, and z. It turns out we get 9, 40, and 41. That's exactly what that triple that we used in the congruent number problem to find the area of 5. So that's a Pythagorean triple. Okay. So now I want to go back to this idea of intersecting curves, because it turns out to be really crucial for the rest of the talk. We're kind of doing this digression on finding Pythagorean triples. That's a very classical and settled matter, and I want to prepare us for talking about some more interesting stuff. So I was claiming that since a line has degree 1, the y and the x are to the first power, and because this has degree 2, that it intersects in 2 points. And you should be very suspicious of that. You might want to stop the video for a second and say, is he really saying any line in any circle always intersect at exactly 2 points? Or any line in any degree 2 curve, if you happen to know other examples of that, intersecting exactly 2 points always? That can't be true. Well, turns out to be true if you interpret it correctly, but that's going to be a little bit of work. So let me show you another example of a line. Here's a very simple line, the x-axis. It's where x can be anything, and y is set to be 0. So it's the y equals 0. That's certainly a degree 1 equation. It's certainly a straight line. A parabola, a pretty simple parabola, is y equals x squared minus 1. If you remember anything about Algebra 2 kind of stuff from high school, parabolas have this general shape. And you can check. You could plug in some x values, like minus 1 gives you 0 for y, x equals 0 gives you minus 1 for y, x equals 1 gives you 0, x equals 2 gives you 3. You can check that this is really an accurate graph of this equation, y equals x squared minus 1. It's definitely degree 2 because the x is squared. It's all about the maximum degree. The y doesn't have to be squared for it to be degree 2. These guys definitely intersect in 2 points. Boom, boom. So that's okay. That's another example of my claim. But this one should look pretty weird. All I did was I changed the minus 1 to a plus 1. It's still the same degree 1 line, a very similar related degree 2 parabola. These don't intersect at all. Or do they? Well, let's actually just follow through the algebra to see what would happen if they did intersect. If they did intersect, there should be one single pair of x and y that satisfy both of these simultaneously. So in other words, there should be an x such that if I plug in y equals 0, that this works. In other words, there should be an x that solves x squared plus 1 equals 0. Or in other words, an x squared that's equal to minus 1. And you might be seeing where this is going. It means that if I allow complex numbers, if I allow x to be plus or minus I, then in fact there is a solution. In fact, there's exactly two solutions. Both plus I and minus I satisfy this equation. I, of course, being the square root of minus 1. Okay, so we need complex numbers here. And I'm not going to talk about complex numbers in any great detail, but in the background of all of this is to make all of this stuff work, all the algebraic geometry that I'm talking very lightly about. You have to use complex numbers to make it work in a pretty nice way. But if you do, then amazing things happen. In particular, suddenly we're rescued and we still get two intersections, the same number. Now, let's push this further. You might have already thought about this with the circle and the line, and thought about like tangency. Suppose I just look at y equals x squared plus 0, just y equals x squared. That is this parabola. This is the utterly standard parabola. This is, if you remember any non-line graph from high school, it's likely to be this one, y equals x squared. That does intersect the x-axis, but at only one point. That doesn't look like 2 points. Well, turns out if we consider a tangential intersection as essentially two infinitely close points, or what's called counting with multiplicity, then we can rescue it. So we have to count tangents specially. And here's one reason. I probably should have another graph of this. I don't think I have it. But just follow my mouse here. If we pull this parabola down just a tiny, tiny, tiny bit, or in other words, we had like y equals x squared minus 0.0001, then we will actually get two intersections, right here and right here, very, very close to each other. And then if we push it back into place, those two intersection points are going to zip coalesce to each other. So there is a really good reason for thinking of this as a reasonable thing. That when you have a tangent, it's almost as if you have two points that are right on top of each other of intersection. And so it really makes a lot of sense to count it with multiplicity. And for a long time, people have known this is the right way to count intersections of curves, but do it with multiplicity. Turns out you can have multiplicity 3 and 4 as well, although not with a degree 2 curve. But I'm not going to show you examples of that. We could, though. It's not that hard. Okay, here's another example of why my statement of always intersecting in 2 points should seem bogus. This is a little bit less of an obvious example. I'm going to change to a different line. The line is still going to have degree 1, of course. Now it's y equals x. That's the 45-degree sloping line. It's got like 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, minus 1, all those points on it. It's the blue line here. And I've got a new degree 2 curve. And so I'm going to ask you, if you're not familiar with hyperbolas, and I'm certainly not assuming that, to believe that the curve defined by x squared minus y squared equals 1 looks like this. These two pieces, and they both go off to infinity in two directions. And the way they go off to infinity is that they go off and they just get closer and closer and closer to this diagonal line, but in fact they never really intersect. And I can show you that. If they did intersect, well, if y is supposed to equal x, that's one of the easiest equations to use in a system of equations where you use one equation against another. It just means that anytime you see a y here, you can substitute in an x because they're supposed to be the same at a point of intersection. So that would mean that x squared minus x squared, which is obviously 0 always, has got to equal 1. Well, that's just not going to happen. So that seems to clearly say that no, these don't intersect. That seems to be finally a real big counterexample to my my conjecture that these guys should always intersect in 2 points. And there's no way complex numbers are going to save you. Complex numbers can't turn 0 into 1. And that's not going to work. But here's what you do. Let's tilt the line down just slightly, like just make it a little less sloped. And I know I should have an animation here, but I didn't go to the trouble of creating an animation. Tilt the line down a little bit so it's a little less steep. It's going to, like, maybe a lot less steep. It's going to intersect here and here. Now tilt it back into place. Maybe it'll intersect here and up here. Now make it even steeper. It'll intersect way down here and way up here. What's happening is those 2 points of intersection are going off to infinity. And so what we do is we actually introduce new points in our space called points at infinity. Let me go to the more simple example of that, the classic example of that, where we actually go back to 2 lines intersecting. Two degree 1 curves, or in other words, 2 straight lines. Usually, if I have 2 straight lines, they intersect in 1 point. But do they always intersect in 1 point? Nope. There's such things as parallel lines. If I have parallel lines, then they don't seem to intersect. But you know what? If I intersect a point at infinity way off in this direction, I can say that those guys really do kind of intersect there. Another way to think about it is take the lines, turn one so that they're not quite parallel anymore, and then slowly turn them back into parallel position. The point of intersection is going to zoom off in a specified direction off to infinity. Similarly here, these guys are going to intersect if you tilt them a little bit so they're not parallel anymore. If you slide them back into position, then I want to say there's a point at infinity that they intersect in. Turns out that this is a really good thing to do. And again, I don't want to go into a really detailed exposition of this, but it turns out that it's a really good thing to introduce a point at infinity and a different one in every direction. Here's the payoff for that, real quick. If you add a point at infinity to the plane in every direction, so a separate point at infinity that way and that way, although I have to say, the point at infinity in this direction, what you do is you say it's exactly the same as the one in the opposite direction. And what you get out of that is a very beautiful thing. We know that in classical geometry, always 2 points determine a line. If you take any 2 points, then you can draw the line between them. And it's most of the time true that 2 lines determine a point by their intersection. But if you don't do this trick of adding points at infinity, you lose an opportunity for a wonderful dualism. You get an exception here and you don't have an exception here. So what we do is we add these points at infinity so that any 2 lines, including parallel lines, intersect in a unique point. And so you get 2 points determine a line and 2 lines determine a point. It's beautifully dual. And it's a wonderfully important thing to do. So if you also use complex numbers and you have this idea of adding these points at infinity, it's called projective geometry. And what you get is finally this theorem. It's called Bazoo's theorem. And I'm probably missing, I think I'm missing an accent on the E. If you use complex numbers, you count intersections with multiplicity, and you work projectively, then it's true that a curve of degree p and a curve of degree q intersect in p times q points. And that's a very, very big theorem about projective geometry. We're going to use that when we go back to the congruent number problem in later parts of this video.